There's something utterly captivating about gazing up at the night sky, isn't there? The endless expanse of stars, the faint glow of distant galaxies, each one a silent reminder of how much we still don't understand about the universe. For centuries, humans have looked to the cosmos with awe and wonder, and yet, despite all our advancements, some of its most profound secrets remain stubbornly out of reach. Even today, with telescopes peering deeper into space than ever before, there are phenomena so bizarre, so utterly inexplicable, that they leave even the most brilliant scientists scratching their heads. These aren't just minor curiosities, they're cosmic riddles that challenge the very foundations of what we think we know. Take, for example, the mysterious signals picked up by radio telescopes, bursts of energy so powerful they can outshine entire galaxies, yet lasting only milliseconds. Or the strange, ghostly structures floating in the void, defying the laws of physics as we understand them. And then there are the objects so dense, so unimaginably massive, that they warp the fabric of space-time itself. These aren't the plot lines of science fiction, they're real, documented enigmas that have researchers around the globe racing to uncover their secrets. What makes these puzzles so fascinating isn't just that they exist, but that every time we think we're close to an answer, the universe throws us another curveball, reminding us just how much we have left to learn. That's exactly what we're diving into today, 30 of the most mind-bending interstellar mysteries that continue to baffle top scientists. From unexplained cosmic anomalies to celestial objects that shouldn't exist according to our current understanding, each one of these puzzles is a doorway into the unknown. Some might hold the key to unlocking new physics, while others could rewrite the story of how our universe works. But one thing's for certain, by the end of this journey, you'll see the night sky in a whole new light. So, let's set aside what we think we know and venture into the great cosmic unknown, where every discovery sparks more questions than answers, and the universe's greatest secrets are still waiting to be uncovered. One of the most tantalizing mysteries in the search for extraterrestrial intelligence began on a quiet August night in 1977. That's when a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary, a burst of radio waves so intense, so unlike anything astronomers had ever seen, that the scientist reviewing the data circled it on the printout and wrote a single word in the margin: "Wow." The signal lasted 72 seconds, just over a minute, but in that brief window, it outshone every other cosmic radio source by a staggering margin. It came from a region near the constellation Sagittarius, with no known stars or planets in its path, and then, just as suddenly as it appeared, it vanished. Despite decades of follow-up observations with increasingly sensitive equipment, the signal was never heard again. What made the WOW signal so baffling wasn't just its strength, it was its frequency. The signal was concentrated at around 1420 MHz, a radio wavelength that's famously quiet because it's shielded from background noise by interstellar hydrogen. It's also a frequency many scientists speculate an advanced civilization might use for communication, since it cuts through the cosmic static. But if it was a message, who or what sent it? Some researchers argue it could have been a natural phenomenon, like a comet's hydrogen cloud or a freak burst of cosmic energy. Others point out that no known celestial object behaves quite like the WOW signal. Then there's the unsettling possibility that it was artificial, a fleeting hello from a civilization far beyond our own, the frustrating truth we may never know. Without a repeat signal, the WOW remains a cosmic one-hit wonder, a whisper from the void that refuses to explain itself. but its legacy endures, reminding us that the universe is full of surprises, and that sometimes the most profound questions linger long after the answers slip away. If the wow signal left us wondering about messages from the cosmos, dark matter presents an even deeper enigma, one that literally shapes the universe around us, yet refuses to reveal itself. Picture this: every galaxy, every cluster of stars we observe spins and moves in ways that defy the laws of gravity as we understand them. The math simply doesn't add up unless there's something out there we can't see. That invisible something is dark matter, an elusive substance that makes up roughly 27% of the universe's total mass and energy. It doesn't emit light, absorb light, or interact with ordinary matter in any way except through gravity. Think of it as the universe's silent scaffolding, holding everything together while remaining utterly invisible to our eyes and instruments. Scientists first stumbled onto this mystery in the 1930s, when astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too quickly to be held together by the gravity of their visible stars alone. Decades later, Vera Rubin's observations of spinning galaxies confirmed that something unseen was exerting a gravitational pull. But what is it? The leading theory suggests dark matter could be made of hypothetical particles called WIMP, weakly interacting massive particles that barely interact with normal matter except through gravity. Yet despite decades of searching, detectors buried deep underground, shielded from cosmic interference, have failed to catch a single definitive WIMP. The puzzle grows stranger when you consider the alternatives. Some researchers propose that dark matter isn't a particle at all, but a sign that our understanding of gravity is incomplete, that Einstein's theory of relativity breaks down on cosmic scales. Others speculate it could be tied to hidden dimensions or even primordial black holes forged in the chaos of the early universe, the most unsettling possibility. Dark matter might not be one thing but many, an entire shadow universe of particles and forces operating just beyond our perception. What makes this mystery so urgent is that dark matter isn't just a cosmic curiosity. It's the glue that holds galaxies together, the force that shaped the universe's structure after the Big Bang. Without it, stars would scatter, and life as we know it might never have formed. Yet after nearly a century of searching, we've yet to catch even a glimpse of it directly. Every experiment that comes up empty forces us to rethink our assumptions, to ask whether we're missing something fundamental about the fabric of reality. One thing's certain: solving the dark matter riddle wouldn't just fill a gap in our textbooks, it could crack open an entirely new chapter in physics, revealing a hidden layer of the universe we never knew existed. Until then, it remains one of science's greatest ghost stories, a reminder that the cosmos is far stranger and far more mysterious than it appears. Imagine a flash of energy so intense it outshines the sun, but only for a fraction of a second. That's the essence of fast radio bursts, or FRB, some of the most fleeting and explosive signals in the universe. First discovered in 2007, these bursts pack more energy than our sun emits in days into a blink and you'll miss it moment, often lasting just milliseconds. What's even stranger, they're coming from galaxies billions of light years away, meaning whatever's causing them must be unimaginably powerful. Yet despite their staggering energy, their origins remain one of astronomy's most stubborn puzzles. The mystery deepens when you consider how unpredictable these bursts are. Some flare once and vanish without a trace, while others repeat at irregular intervals, like a cosmic Morse code with no discernible pattern. One particularly famous repeater, known as FRB 121811, has been erupting sporadically since its discovery, giving scientists rare opportunities to study it. But even with these repeating signals, the source remains maddeningly unclear. Some theories point to extreme astrophysical objects like magnetars, a type of neutron star with a magnetic field trillions of times stronger than Earth. When these stars undergo starquakes or magnetic eruptions, they could unleash bursts of radio waves powerful enough to reach across the cosmos. Then there's the wildcard possibility: could some FRBs be artificial? The idea isn't as far-fetched as it sounds. The sheer energy required to produce these bursts would demand technology far beyond our own. But if an advanced civilization were, say, powering interstellar light sails or transmitting signals across galaxies, the byproduct might look eerily similar to an FRB. Of course, most scientists lean toward natural explanations, but the fact that we can't rule out any scenario speaks volumes about how little we truly understand. What makes FRBs so tantalizing isn't just their mystery, it's what they reveal about the universe. As these waves travel across space, they interact with the sparse matter between galaxies, leaving faint imprints that astronomers can decode like cosmic breadcrumbs. This lets scientists map the universe's hidden structure, measuring the distribution of matter we'd never see otherwise. In a way, FRBs are both the question and the tool to help answer it. Yet for all their potential, these bursts remain elusive. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are scanning the skies around the clock, catching dozens of FRBs every month. But each discovery seems to raise more questions than it answers. Are all FRBs created equal, or do different types hint at multiple origins? Could some be the death cries of collapsing stars, while others are the hum of distant, hyper-advanced engines? One thing's certain: every time we detect another burst, it's a reminder of how dynamic, how alive the universe really is. Out there in the darkness, forces beyond our comprehension are at work, sending whispers across the cosmos, and we're only just beginning to listen. We've scoured the cosmos for signs of life, built telescopes capable of peering into distant star systems, and even sent messages into the void, yet the universe remains eerily silent. This glaring contradiction is at the heart of the Fermi Paradox, a puzzle that's haunted scientists since physicist Enrico Fermi famously asked, "Where is everybody?" If the universe is so vast with billions of Earth-like planets, why haven't we encountered a single whisper of extraterrestrial intelligence? One of the most unsettling explanations is the Great Filter theory, the idea that some catastrophic barrier prevents life from advancing beyond a certain point. Maybe the filter lies in the past, meaning the emergence of life itself is so astronomically rare that we're essentially alone. Or worse, it could still be ahead of us, lurking in humanity's future. Disease, nuclear war, environmental collapse, any of these could be the hurdle that wipes out civilizations before they ever reach the stars. The chilling implication. If the filter is still ahead, we might be doomed to vanish before ever making contact. But not all theories are so bleak. Some suggest advanced civilizations might simply be avoiding us, either by design or because their technology operates in ways we can't perceive. Imagine ants trying to comprehend the internet. Human communication might be as invisible to them as an alien civilization's signals could be to us. Others propose that spacefaring societies could be deliberately hiding, fearing the dangers of contact with less advanced species. After all, history shows what happens when technologically superior civilizations encounter others. It rarely ends well for the underdog. Then there's the zoo hypothesis, the notion that Earth is intentionally isolated, a cosmic nature preserve where intelligent life is observed but not disturbed. It's a strange thought, but no stranger than the silence we've encountered so far. And let's not forget the possibility that we're simply too early, that the universe is still young, and we're among the first civilizations to arise, with others yet to emerge in the trillions of years ahead. The Fermi Paradox forces us to confront uncomfortable questions about our place in the cosmos. Are we special or just lucky, alone or merely unheard? With every exoplanet discovered and every silent radio telescope scan, the mystery deepens. Until we find definitive answers, the paradox remains a humbling reminder that for all our searching, the universe still guards its secrets closely. Of all the stars in our galaxy, few have captured scientists' imaginations and sparked wild theories quite like KIC 8462852, better known as Tabby's star. Named after astronomer Baryon, who first brought its bizarre behavior to light, this distant sun behaves like nothing else we've ever seen. Most stars flicker gently as planets pass in front of them, but Tabby's star doesn't just dim, it plummets, dropping in brightness by up to 22% at irregular intervals. These aren't the predictable dips caused by orbiting worlds. Instead, the star's light fades in chaotic, asymmetrical patterns, as if something vast and misshapen is drifting across its surface. When the data first emerged from NASA's Kepler Space Telescope in 2015, astronomers scrambled for explanations. The leading theory, a colossal swarm of comets, thousands of them, might be circling the star in tight formation, their dusty tails blotting out its light in unpredictable waves. But there's a problem. Comets on that scale would require an unimaginable amount of material, far more than our own solar system could muster. Even then, the dips in brightness are too extreme, too jagged to fit neatly into that model. That's when things got even stranger. Archivists digging through old photographic plates discovered something shocking. Tabby's star appears to have been gradually dimming over the past century, fading by an astonishing 14% between 1890 and 1989. Stars simply don't behave this way. They're supposed to shine steadily for billions of years. So what could possibly explain this slow, eerie decline? Cue the most provocative theory of all, alien megastructures. Specifically, a hypothetical Dyson swarm, a vast array of energy-collecting satellites or panels built by an advanced civilization to harness their star's power. The idea, first proposed by physicist Freeman Dyson in the 1960s, suggests that a sufficiently advanced society might dismantle planets to construct these orbiting solar farms, creating irregular shadows as they pass in front of their sun. It's a tantalizing thought, and for a brief moment, Tabby's star seemed like the best candidate yet for evidence of extraterrestrial engineering. But science thrives on skepticism, and follow-up studies have chipped away at the alien hypothesis. Spectroscopic analysis revealed no signs of artificial heat signatures, and further observations showed the dimming varies across different wavelengths, something a solid megastructure wouldn't do. Instead, the culprit might be something far more mundane, yet still bizarre. Clouds of fine, interstellar dust, possibly from a recent planetary collision or a disintegrating moon. Even so, no single explanation fits all the data perfectly, leaving the door cracked open for more exotic possibilities. What makes Tabby's star so compelling isn't just the mystery, it's the way it forces us to question our assumptions. Here's an object that defies every standard classification, challenging astronomers to think beyond textbooks and consider scenarios that border on science fiction. Whether it's comets, dust, or something we haven't even imagined yet, this star reminds us that the universe is full of surprises, and that sometimes the most ordinary-looking dot in the sky can hide the most extraordinary secrets. And the search isn't over. Every new observation, every fresh analysis brings us closer to unraveling the puzzle. One day, we might finally understand what's lurking around Tabby's star. Until then, it stands as a beacon of cosmic curiosity, a reminder that even in an age of cutting-edge telescopes, the universe still has a few tricks up its sleeve. Deep in the cosmic void, something massive is pulling us, and everything around us toward an unseen destination at over 2 million kilometers per hour. This invisible force, known as the Great Attractor, has been tugging galaxies, including our own Milky Way, toward a mysterious point in space for billions of years. The strangest part, we can't see what's doing it. Hidden behind the thick dust and stars of our galaxy's central plane, this gravitational anomaly remains one of the universe's most tantalizing enigmas. The story begins in the 1970s when astronomers mapping the motions of galaxies noticed something peculiar. Instead of drifting apart evenly as the universe expands, entire clusters, including our local group of galaxies, were streaming toward a specific region in the constellation Centaurus. The sheer scale of this motion defied explanation. Whatever lay at the center of this pull had to be unimaginably massive, with the gravitational heft of tens of thousands of Milky Ways. But when scientists pointed their telescopes in that direction, they found nothing, or at least nothing that could account for such a tremendous force. Here's the catch. Our view of the Great Attractor is blocked by what astronomers call the zone of avoidance, a dense band of gas, dust, and stars along the Milky Way's disk that obscures nearly 20% of the night sky. It's like trying to spot a lighthouse through a blizzard. Even X-ray and infrared telescopes, which can pierce some of this cosmic fog, struggle to reveal what's lurking behind it. Early theories proposed a single, colossal supercluster of galaxies as the culprit, but later observations showed the mass there, while significant, wasn't nearly enough to explain the pull. Then came an even bigger revelation. In the 21st century, astronomers discovered that the Great Attractor itself is being pulled toward something far more immense, a mind-boggling structure called the Shapley supercluster, the largest known concentration of matter in our cosmic neighborhood. This supercluster, located over 650 million light-years away, contains thousands of galaxies packed into a region so dense it warps space-time around it. But even Shapley might not be the end of the story. Some researchers speculate an even grander attractor could lie beyond it, a cosmic Matryoshka doll of gravitational mysteries. So what is the Great Attractor? The leading theory suggests it's not a single object but a vast confluence of dark matter, galaxies, and galaxy clusters, a gravitational nexus where the universe's hidden scaffolding converges. Dark matter's invisible tendrils could be weaving through this region, amplifying its pull in ways we don't yet understand. Others wonder if exotic phenomena, like primordial black holes or defects in the fabric of space-time left over from the Big Bang, might play a role. What makes this mystery so gripping is its scale. The Great Attractor isn't just a curiosity, it's rewriting the map of our cosmic neighborhood, revealing how galaxies move in ways we never anticipated. Every new observation peels back another layer, showing us how much we've yet to learn about the forces shaping the universe. And as our telescopes grow more powerful, we might finally glimpse what's been hiding in the shadows all along, a reminder that sometimes the universe's biggest secrets are hiding in plain sight, just beyond our line of view. Sometimes the universe throws us a curveball so subtle that it takes decades to notice, like the strange case of the Pioneer Anomaly. Back in the 1980s, as NASA's twin probes Pioneer 10 and Pioneer 11 ventured beyond the solar system, something peculiar happened. These spacecraft, which had already made history by becoming the first human, made objects to travel past the asteroid belt and send back stunning images of Jupiter and Saturn, began slowing down in a way that defied all predictions. The deceleration was tiny, just a fraction of a nanometer per second squared, but over the vast distances of space, even the slightest deviation adds up. By the time scientists spotted the discrepancy, the probes were hundreds of millions of kilometers off course. At first, researchers assumed it must be a simple engineering quirk, perhaps residual fuel leaking from the spacecraft or heat radiating unevenly from their nuclear power sources. But when they crunched the numbers, nothing quite fit. Thermal radiation could explain part of the anomaly, but not all of it. The probes were experiencing a drag that shouldn't exist, as if some invisible hand were gently tapping the brakes on their journey into the cosmos. That's when the theories got interesting. Could this be evidence of a flaw in our understanding of gravity? Einstein's theory of general relativity has been tested relentlessly, and it's held up under nearly every condition. But what if, in the vast emptiness between stars, the rules bend in ways we haven't anticipated? Some physicists speculated that the anomaly might hint at exotic ideas like modified gravity or even the influence of unseen dimensions. Others wondered if dark matter, that elusive cosmic ghost, could be clustering in ways that subtly alter the motion of spacecraft. Then there's the wildcard possibility. The Pioneer Anomaly might not be an anomaly at all. Later missions like New Horizons, the probe that flew past Pluto, didn't exhibit the same unexpected slowdown. Was Pioneer's deceleration a unique artifact of its design, or did those later spacecraft simply travel through a different patch of space where the mysterious effect wasn't present? The frustrating truth is we may never know for sure. Both Pioneer 10 and 11 have fallen silent, their signals lost to the void as they continue their endless drift among the stars. But their legacy lives on in the questions they left behind. The Pioneer Anomaly stands as a humbling reminder that even our most trusted laws of physics might have blind spots, tiny cracks in the foundation where the universe's secrets slip through. What makes this mystery so compelling isn't just the unsolved puzzle itself, but what it represents. The idea that even in the era of precision spaceflight, the cosmos can still surprise us. Every time we think we've got it all figured out, some small, unexplained glitch whispers that there's more to learn. And who knows, the next spacecraft we send into the deep might just stumble upon another one of these cosmic breadcrumbs, leading us closer to truths we haven't even imagined yet. In October 2017, astronomers spotted something extraordinary, a visitor from beyond our solar system, tumbling through space at breakneck speed. Named Oumuamua, Hawaiian for scout, this strange object was unlike anything we'd ever seen. Its elongated, cigar-like shape, stretching nearly a quarter-mile long but only a tenth as wide, defied the usual round or lumpy forms of asteroids and comets. And then came the real shock. As it slingshotted past the sun and headed back into interstellar space, it didn't just coast, it accelerated, as if propelled by some unseen force. At first, scientists scrambled to explain the acceleration with natural causes. Comets, for example, speed up when their icy surfaces vaporize in the sun's heat, creating a faint jet of gas. But Oumuamua showed no signs of this outgassing, no telltale coma or tail. Its surface appeared strangely barren, reflecting sunlight with a metallic sheen more akin to an asteroid. Yet something was undeniably pushing it forward. The leading theory, maybe it was outgassing, just in a way we couldn't detect. Perhaps hidden jets of gas erupted from cracks in its surface, too faint for our telescopes to spot. But even this explanation felt like forcing a puzzle piece where it didn't quite fit. That's when the speculation took a wilder turn. Harvard astronomer Avi Loeb famously floated the idea that Oumuamua could be artificial, a light sail perhaps drifting from another star system. Light sails, thin sheets designed to catch the momentum of starlight, are a real technology humans are testing for interstellar travel. Could Oumuamua have been a relic of some advanced civilization, a discarded probe or a derelict vessel? The idea sent ripples through the scientific community, with some calling it premature, others daring to wonder. But the truth is, we'll likely never know for sure. By the time we spotted Oumuamua, it was already racing away, too distant for a closer look. Its brief visit left us with more questions than answers. Was it a shard of a shattered planet ejected from another star system? A cosmic iceberg venting hydrogen too subtle for our instruments to detect? Or something even more extraordinary, a fragment of technology from a world we can't yet imagine? What makes Oumuamua so haunting isn't just its mystery, it's the realization that interstellar visitors might be far more common than we thought. In the years since, we've spotted other objects likely from beyond our solar system, like the comet Borisov in 2019. But none have behaved quite like Oumuamua. It remains a singular enigma, a fleeting glimpse into the vast and uncharted diversity of the cosmos. Every time we think we've categorized the universe's objects, something like this comes along to remind us the universe doesn't play by our rules. And perhaps, just perhaps, the most extraordinary discoveries aren't the ones we're looking for, but the ones we never saw coming. We like to think we've got a pretty good handle on what the universe is made of: stars, planets, gas, dust. But here's the cosmic plot twist: about half of the normal matter in the universe has gone missing. Not dark matter, not some exotic particle, but the ordinary stuff: protons, neutrons, electrons, the building blocks of everything we can see and touch. Scientists call this the missing Baryon problem, and it's one of the most baffling accounting errors in modern astrophysics. The mystery began when researchers tallied up all the visible matter in the universe: stars, galaxies, the glowing gas between them, and compared it to the amount predicted by the Big Bang's afterglow, the cosmic microwave background. The numbers didn't match, not even close. According to those primordial echoes, there should be nearly twice as much ordinary matter out there as we've been able to find. So where is it all hiding? One leading theory points to the cosmic web, the vast, invisible scaffolding of the universe. This web is made of thread-like filaments of hot, diffuse gas stretching millions of light-years between galaxies. These filaments are so tenuous, so spread out, that they're nearly impossible to spot with traditional telescopes. Imagine trying to see a single light bulb floating in the Grand Canyon. That's the scale of the challenge. But recent breakthroughs in X-ray and ultraviolet astronomy have given us glimpses of this hidden realm. By studying how light from distant quasars filters through these filaments, scientists have detected traces of the missing matter, like catching the shadow of a ghost. Yet even these detections only account for a fraction of the total. The rest could be lurking in even more elusive forms, perhaps as ultra-hot plasma in intergalactic space, or as rogue atoms drifting in the voids between galaxy clusters. Some researchers speculate that the missing baryons might be tied up in faint, undetectable dwarf galaxies, or as part of vast, cold clouds of molecular gas. Others wonder if our instruments simply aren't sensitive enough yet to catch the faint whispers of this matter, scattered across the universe in ways we haven't even imagined. What makes this puzzle so important is that it's not just about filling in a cosmic spreadsheet. The missing baryons are key to understanding how the universe evolved. They're the raw material for stars, planets, and life itself. Without them, our models of cosmic structure, how galaxies form, how clusters merge, start to unravel. It's like trying to bake a cake with only half the flour the recipe calls for. You might end up with something, but it won't be what you expected. The search for these lost baryons is far from over. New telescopes, like the upcoming European Space Agency's Athena mission, are designed to probe these faint signals with unprecedented precision. Every discovery brings us closer to balancing the cosmic books, but for now, the universe's missing matter remains one of its quietest, most persistent enigmas. It's a reminder that even the ordinary can hide in plain sight, and that sometimes the biggest mysteries aren't about the strange and exotic, but about the stuff we thought we knew all along. There's a quiet unease among cosmologists, a nagging feeling that something fundamental might be missing from our picture of the universe, and it all traces back to an eerie pattern in the oldest light we can see. The cosmic microwave background, or CMB, is often called the afterglow of the Big Bang, a snapshot of the universe just 380,000 years after its birth. Studied in meticulous detail by satellites like Planck and WMAP, this faint radiation should be uniformly speckled, a random scatter of hot and cold spots reflecting the primordial seeds of galaxies. But in 2005, scientists noticed something that sent a chill down the spines of theorists. The CMB isn't as random as it should be, dubbed the axis of evil by researchers partly for its defiance of standard cosmology, partly for the ominous nickname's shock value. This anomaly describes a bizarre alignment in the CMB's fluctuations. Across vast swaths of the sky, the hot and cold spots seem to line up along a particular axis, as if the early universe had a preferred direction. That shouldn't happen. The cornerstone of modern cosmology is the principle of isotropy, the idea that the universe on large scales looks the same in all directions. The axis of evil challenges that assumption, hinting at a cosmic asymmetry that defies our most basic expectations. Theories attempting to explain it range from the mundane to the mind-bending. On the cautious end, some argue it's just statistical noise, a fluke in how we're interpreting the data. After all, the universe is vast, and even random distributions can sometimes appear oddly structured by chance. Others suggest it might be an artifact of our own motion through space, a kind of cosmic Doppler effect distorting our view. But the more provocative explanations, they're the stuff of paradigm shifts. One startling possibility is that the axis of evil is a fossil, a relic of something that existed before the Big Bang. Could the universe we see today have inherited structure from an earlier epoch, a pre-Big Bang reality that imprinted its geometry onto our cosmos? It's a radical idea, but proponents point to theories like conformal cyclic cosmology, where universes cycle through endless expansions and contractions, each leaving faint traces in the next. If true, the axis might be a crack in the door to a past we thought was forever lost. Then there's the multiverse angle. In some interpretations of string theory, our universe is just one bubble in an infinite froth of others. If we're nestled close to another bubble's edge, its gravitational influence could have nudged our early universe into an unexpected alignment. It's a long shot, but the stakes are high. Proof of a multiverse would rewrite not just cosmology, but our very understanding of reality. What makes the axis of evil so unsettling isn't just the anomaly itself, but what it represents, a crack in the foundation of modern physics. For decades, the CMB has been the gold standard for testing our theories, its near-perfect uniformity a triumph of the Big Bang model. Now, with this unexplained axis lurking in the data, scientists are forced to confront an uncomfortable truth that the universe might not be as uniform or as predictable as we've always assumed. The debate is far from settled. New missions like the proposed CMB S4 experiment aim to map the microwave sky with unprecedented precision, hunting for clues that might confirm or debunk the axis once and for all. Until then, it remains one of cosmology's most tantalizing loose ends, a whisper from the dawn of time that refuses to fit neatly into our theories. Whether it's a statistical mirage or a glimpse of deeper physics, one thing's certain: the universe still has a few surprises left, and they're hiding in the oldest light there is. If there's one law of physics that seems unbreakable, it's this: information can never be destroyed, not just in the practical sense, like burning a book and losing its words, but at the deepest quantum level. Every particle, every interaction leaves an imprint on the universe, a trail of cause and effect that, in theory, could be traced backward like an unbroken chain. But black holes, they don't just bend the rules, they shatter them. According to Einstein's general relativity, when matter falls into a black hole, it's gone for good, crushed into a singularity where space and time cease to exist as we know them. No trace, no record, no way to reconstruct what fell in. And that creates a paradox so profound it's kept physicists arguing for decades. At the heart of the puzzle is a clash between two titans of physics, quantum mechanics and general relativity. Quantum mechanics insists that information is immutable even if you burn that book. Its information is still encoded in the smoke and ashes, just scrambled beyond recognition. But general relativity paints a bleaker picture for black holes. As Stephen Hawking famously showed, black holes aren't entirely black. They slowly leak energy, radiating away over eons in what we now call Hawking radiation. Here's the catch: that radiation appears to be completely random, carrying no information about what fell inside. So when the black hole finally evaporates, all traces of its meal, stars, planets, even entire civilizations, seem to vanish without a whisper. This contradiction, known as the black hole information paradox, isn't just a philosophical headache. It suggests a fundamental flaw in our understanding of reality. If information can be destroyed, then quantum mechanics, the framework underlying everything from atoms to computers, is wrong. If it can't, then general relativity's description of black holes must be missing something crucial. Enter some of the wildest ideas in modern physics. One leading proposal is the firewall hypothesis, which suggests that just inside a black hole's event horizon, there's a searing wall of energy that obliterates anything crossing it, preserving information by encoding it in the radiation. But this comes with its own problems, like violating Einstein's principle that free-falling observers should notice nothing unusual as they cross the horizon. Then there's the holographic principle, a mind-bending idea that all the information falling into a black hole isn't lost but smeared across its two-dimensional surface like a cosmic fingerprint, encoded in ways we don't yet understand. It's as if the universe keeps a backup copy, a safeguard against total erasure. And let's not forget string theory's take, that black holes might be tangled knots of vibrating strings, with information woven into their very fabric, escaping slowly as they unravel. What makes this paradox so captivating isn't just the intellectual tug-of-war, it's the stakes. Solving it could crack open a unified theory of quantum gravity, finally bridging the gap between the very large and the very small. Every proposed solution forces us to rethink the nature of space, time, and information itself. So far, no answer has satisfied everyone, but perhaps that's the point. The black hole information paradox isn't just a puzzle to solve, it's a beacon guiding us toward deeper truths about the universe. And until we find those truths, black holes will remain the ultimate cosmic locks, guarding their secrets behind event horizons we're only beginning to comprehend. Earth's moon seems like a quiet, lifeless place today, but buried in its ancient rocks lies evidence of a surprisingly turbulent past, one of the most baffling clues. The moon once had a magnetic field, possibly even stronger than Earth's at times. That shouldn't be possible. Magnetic fields are typically generated by molten metal churning in a planet's core, creating a dynamo effect. But the moon's core is small and mostly solid, far too feeble to power such a robust field. So how did our closest celestial neighbor pull off this cosmic magic trick? The mystery deepened when Apollo astronauts brought back lunar samples in the 1960s and 70s. Locked inside those rocks were tiny magnetic signatures, proof that the moon's field lasted for over 1 billion years, far longer than its core could have stayed molten under conventional models. Some of the oldest samples suggest the field peaked around 3.5 billion years ago, reaching intensities comparable to Earth's today. That's like finding a candle that somehow burned as bright as the sun. Scientists have scrambled for explanations, and the theories are as creative as they are contentious. One idea points to massive asteroid impacts in the moon's youth. Imagine a colossal collision, so violent it temporarily liquefied the moon's mantle, stirring up enough motion to jumpstart a short-lived dynamo. Others propose that the moon's orbit once brought it much closer to Earth, where tidal forces stretched and heated its interior like putty, creating the necessary fluid motion. There's even a hypothesis that radioactive elements decaying deep within the moon could have provided the heat needed to keep things churning. But here's the twist: none of these explanations fully fit the data. Impact-driven dynamos would flicker on and off, yet the moon's field appears to have been surprisingly stable. Tidal heating might explain an early field, but not why it persisted for so long. And while radioactivity can generate heat, it's unclear whether it could sustain the precise motions needed for a dynamo. The more we learn, the more the moon's magnetic past seems to defy every rulebook. What makes this puzzle so crucial isn't just about the moon, it's about rewriting the story of how planetary magnetic fields work. If a small, seemingly inert body like the moon could generate a strong field without a traditional dynamo, what does that mean for other rocky worlds? Could Mars, now barren and silent, have once harbored a similar surprise? Might exoplanets we've written off as lifeless actually hide magnetic shields of their own? The implications stretch beyond astrophysics. Earth's magnetic field is our silent guardian, deflecting deadly solar radiation and preserving our atmosphere. Understanding how other worlds lose or gain their magnetic protection could reshape how we search for habitable planets. The moon, our constant companion, might just hold the key to unlocking mysteries far beyond its dusty surface. For now, the question lingers unanswered. Future missions like NASA's planned Lunar Geophysical Network aim to probe the moon's interior with unprecedented precision, hunting for echoes of its magnetic heyday. Until then, those ancient rocks remain cryptic time capsules, whispering secrets about a moon that was far more dynamic, far more enigmatic than the pale orb we see today. And perhaps that's the most humbling lesson of all. Even the familiar can be stranger than we ever imagined. There's a place in the universe so empty, so unsettlingly vast, that astronomers call it the Great Nothing. Officially known as the Boötes Void, this enormous region of space stretches an astonishing 330 million light-years across, yet it contains almost nothing. No galaxies, no stars, just a chilling expanse of near-perfect emptiness. To put that in perspective, if our Milky Way were placed at one edge of the void, the nearest major galaxy on the other side would be so distant, its light would take hundreds of millions of years to reach us. This isn't just a quiet corner of the cosmos, it's a cosmic desert on a scale that defies everything we thought we knew about how the universe organizes itself. The Boötes Void was discovered in the 1980s during a survey of galaxy distributions, and its existence sent shockwaves through the astronomical community. According to our best models, matter in the universe should be arranged in a vast web-like structure, with dense clusters of galaxies connected by filaments and separated by smaller, expected gaps. But the Boötes Void isn't just a gap. It's a staggering abyss, a bubble of nothingness so large that it shouldn't exist under standard cosmology. If the universe were a bustling city, This would be a vacant lot the size of a continent. So how did such a void form? One possibility is that it's the result of an ancient cosmic collision, not between objects, but between competing forces in the early universe. In the chaotic aftermath of the Big Bang, regions of slightly lower density might have expanded faster, pushing matter outward and leaving behind these vast empty pockets. Another theory suggests the void could be evidence of something even more exotic, a tangle of dark energy. The mysterious force accelerating the universe's expansion might have acted like a cosmic vacuum, clearing out galaxies over billions of years. But here's where things get even stranger. The Boötes Void isn't entirely empty. A handful of galaxies, fewer than 60, have been found drifting in this colossal nothingness like lone ships on an endless ocean. These isolated galaxies raise another question. Did they somehow get left behind, or are they the survivors of a much larger population that mysteriously vanished? Some researchers speculate that these galaxies might be surrounded by invisible dark matter halos, anchoring them in place while ordinary matter was swept away. Others wonder if the void is still evolving, its emptiness growing as the universe expands, leaving these few galaxies as the last witnesses to a disappearing act we don't yet understand. What makes the Boötes Void so haunting isn't just its size, it's the way it challenges our assumptions. The universe isn't supposed to have holes this big. If voids like this are more common than we thought, it could mean our models of cosmic structure need a serious overhaul. Or worse, it might hint at forces or phenomena we haven't even discovered yet. Every time we point our telescopes at this great nothing, we're reminded that the universe isn't just full of wonders, it's full of absences too. And sometimes the most profound mysteries aren't about what's there, but what isn't. Imagine measuring the same thing with two different rulers and getting wildly different answers every time. That's essentially the crisis cosmologists are facing with the Hubble Tension, a stubborn discrepancy that's shaking the foundations of modern astronomy. At its core, it's a simple question: how fast is the universe expanding? But the answers we're getting depend entirely on how we measure them, and the numbers refuse to line up. For decades, scientists have relied on two primary methods to calculate the Hubble constant, the rate of the universe's expansion. The first method looks at the cosmic microwave background, the faint glow left over from the Big Bang. By analyzing tiny fluctuations in this ancient light, researchers can extrapolate how quickly the universe should be expanding today. The second method uses pulsating stars called Cepheids and cataclysmic supernovae in nearby galaxies, measuring their distances and speeds to gauge the expansion rate directly. Both approaches are meticulous, both are backed by mountains of data, and yet they disagree by about 10%. That might not sound like much, but in the precision-driven world of cosmology, it's a gap wide enough to drive a paradigm shift through. The implications are staggering. If the discrepancy is real and not just some systematic error, it could mean our understanding of the universe's composition is fundamentally flawed. Maybe dark energy, the mysterious force accelerating the expansion, isn't constant but changes over time. Perhaps there's an unknown particle, a relic from the early universe, subtly altering the cosmic balance. Some theorists even speculate that gravity itself might behave differently on the largest scales, bending the rules in ways Einstein never anticipated. What makes the Hubble tension so electrifying isn't just the conflict, it's the stakes. This isn't a minor accounting error. It's a potential crack in the standard model of cosmology, the framework that's guided our understanding of the universe for decades. Every new observation, from the James Webb Space Telescope's razor-sharp infrared vision to next-generation CMB experiments, is scrutinized for clues. Could this be the anomaly that leads us to a deeper theory, one that unites gravity and quantum mechanics? Or will it vanish under closer scrutiny, leaving us with a nagging sense that we missed something obvious? For now, the tension remains unresolved, a tantalizing riddle written in the stars. It's a reminder that even our most trusted cosmic yardsticks might need recalibrating, and that the universe, as always, has a few surprises left up its sleeve. Hidden in the faint glow of the cosmic microwave background, there's a cold spot so vast and so unusual that it defies easy explanation. Known as the Eridanus Supervoid, this mysterious region stretches nearly 2 billion light-years across, an incomprehensible emptiness where the temperature of the primordial universe's afterglow dips lower than it should. At first glance, it might seem like a statistical fluke, a random blip in the data, but the odds of such a cold spot forming by chance are astronomically low, roughly 1 in 50,000. That's like rolling a die and getting the same number 1,000 times in a row. Clearly, something strange is at work here. What makes this cosmic chill so puzzling isn't just its size, it's the way it clashes with our leading theories of the universe's birth. According to inflation theory, the rapid expansion of the early universe should have left behind a fairly uniform distribution of hot and cold spots in the CMB. The Eridanus Supervoid, with its extreme coldness, throws a wrench into that tidy picture. If voids this large can form naturally, it might mean inflation didn't happen quite the way we think, or that something even more exotic is going on. One leading explanation suggests the supervoid could be just that, an enormous, mostly empty region of space where the lack of matter subtly cools the CMB photons passing through it. Think of it like walking through a windless valley on a cold night. The absence of warmth makes the air feel colder. But here's the catch. Even the largest known voids shouldn't produce a temperature drop this dramatic. The Eridanus Supervoid would need to be far emptier, far larger, or somehow fundamentally different from any void we've observed before. That's where things get wild. Some theorists propose that this cold spot might not be a void at all, but evidence of a collision with another universe. In certain multiverse models, our cosmos could be one bubble among countless others in an infinite foam of realities. If a neighboring bubble universe brushed against ours in the distant past, the energy released could have left a scar, an imprint of that encounter frozen in the CMB. It's a radical idea, but the sheer scale of the anomaly demands radical solutions. Then there's the possibility of entirely new physics. Could dark energy, the mysterious force accelerating the universe's expansion, behave differently in this region? Or might there be some exotic form of matter or energy, still unknown to science, warping the fabric of space-time in ways we can't yet explain? The Eridanus Supervoid is more than just a curiosity. It's a potential window into realms of physics we've never imagined. For now, the mystery endures. New telescopes and sky surveys are scrutinizing this enigmatic cold spot, searching for clues that might tip the scales toward one explanation or another. But whether it's a cosmic void, a multiverse fingerprint, or something even stranger, one thing is certain. The Eridanus Supervoid reminds us that the universe still holds profound secrets. And sometimes the coldest corners of space might just be hiding the hottest discoveries. Far beyond the orbit of Neptune, where sunlight is reduced to a faint glimmer and temperatures plunge to near absolute zero, something massive may be silently shaping the orbits of distant celestial bodies. This is the tantalizing mystery of Planet 9, a hypothetical world up to 10 times more massive than Earth, lurking in the frozen outskirts of our solar system. The evidence for its existence isn't direct. No telescope has yet captured its faint glow, but the gravitational fingerprints it leaves behind are impossible to ignore. The story begins with a group of small, icy objects in the Kuiper Belt, a vast ring of debris left over from the solar system's formation. These objects don't orbit the sun randomly. Instead, their paths cluster in peculiar, elongated trajectories that tilt at angles unlike anything else in the solar system. Statistically, the odds of this happening by chance are less than 1 in 15,000. It's as if an unseen hand were herding them into these strange alignments. In 2016, astronomers Konstantin Batygin and Mike Brown proposed that only one thing could explain this odd behavior: a distant, undiscovered planet, its gravity sculpting these orbits over billions of years. But if Planet 9 is real, why haven't we found it yet? The search is like looking for a single dim light bulb in a city the size of a continent. Current estimates place it anywhere between 300 and 800 times farther from the Sun than Earth, meaning it reflects virtually no sunlight. Even our most powerful telescopes would struggle to spot it unless we knew exactly where to look. And that's the catch. Without knowing its precise orbit, astronomers must scan vast swaths of sky, a painstaking process that could take years. The intrigue doesn't stop there. Some researchers suggest Planet 9 might not be a traditional planet at all. Could it be a primordial black hole, no larger than a grapefruit but with the mass of a world, warping space-time as it drifts unseen? Others speculate it might be a rogue planet captured by the Sun's gravity after being flung from another star system. Then there's the more unsettling possibility: what if it's not alone? Simulations hint that multiple distant planets could be lurking out there, rewriting our understanding of the solar system's architecture. The hunt continues, with every new discovery adding another piece to the puzzle. Recent observations of extreme trans-Neptunian objects, icy bodies with bizarre, looping orbits, only deepen the mystery. Some of these objects swing so far out that they take tens of thousands of years to complete a single trip around the Sun, their path seemingly tugged by something unseen. Each one is another breadcrumb leading us closer to or further from the truth. What makes this search so compelling isn't just the potential discovery of a new planet. It's the realization that our cosmic neighborhood might still hide worlds of staggering scale, silently shaping the dance of the solar system from the shadows. Whether Planet 9 is confirmed or debunked, the quest itself has already reshaped our understanding of the solar system's outer limits, proving that even in our own backyard, the universe still keeps secrets waiting to be uncovered. Deep in the heart of our Milky Way, a storm of gamma rays rages, an unexplained torrent of high-energy light that shouldn't exist. Dubbed the galactic center excess, this mysterious glow has baffled astronomers since its discovery in the data from NASA's Fermi Gamma-Ray Space Telescope. The Milky Way's core is already a chaotic place, packed with swirling gas, violent star formation, and a supermassive black hole. But even after accounting for all these known sources, there's still a surplus of gamma rays, a relentless, diffuse energy that refuses to fit into any conventional explanation. What makes this excess so puzzling is its peculiar signature. The gamma rays aren't clustered around specific points, as you'd expect from pulsars or other compact objects. Instead, they're spread across a wide region like a faint, glowing fog permeating the galactic center. When scientists modeled every known astrophysical process, colliding cosmic rays, dying stars, even the supermassive black hole Sagittarius A, none could fully account for the signal. That left researchers with two electrifying possibilities. Either we're seeing the fingerprints of an entirely new celestial phenomenon, or we're staring directly at evidence of dark matter's hidden nature. The dark matter angle is especially tantalizing. According to leading theories, dark matter particles might annihilate when they collide, converting their mass into bursts of gamma rays. If true, the galactic center where dark matter is thought to be densest would be the perfect place to spot this elusive process. The energy spectrum of the excess even roughly matches predictions for certain types of dark matter particles like WIMP. It's a compelling case, but not without its skeptics. Some argue that the signal could just as easily come from a population of undiscovered millisecond pulsars, ancient, rapidly spinning neutron stars too faint to detect individually but collectively bright enough to mimic the excess. The debate hinges on a cosmic game of hide and seek. To prove the pulsar theory, astronomers would need to resolve thousands of these dim objects in the galactic center, a task currently beyond our telescope's capabilities. Meanwhile, dark matter proponents are refining their models, searching for telltale patterns in the gamma-ray data that could definitively rule out astrophysical sources. It's a high-stakes puzzle because if the excess is from dark matter, it would be the first direct clue to its identity after decades of searching. But there's a twist. Recent studies have added yet another layer to the mystery. Some analyses suggest the excess isn't perfectly symmetrical. It might be slightly lopsided, a detail that doesn't neatly fit either the dark matter or pulsar scenarios. Could there be an entirely different explanation, something we haven't even considered? The possibilities range from exotic physics, like primordial black holes evaporating into gamma rays, to more mundane but overlooked sources, like rogue stars colliding in the galactic bulge. The galactic center excess is more than just an anomaly, it's a cosmic Rorschach test, revealing how much we still don't know about the universe's most fundamental ingredients. Every new observation, from next-generation gamma-ray telescopes to ultra-sensitive dark matter detectors, brings us closer to an answer. But for now, the heart of our galaxy keeps its secrets, radiating questions instead of light. And that's the beauty of it. Sometimes the most profound discoveries begin with something we can't explain. Just beyond Pluto, in the frozen reaches of our solar system, there's a boundary so abrupt it defies everything we know about how planetary systems form. Astronomers call it the Kuiper Cliff, a mysterious drop-off where the number of icy objects in the Kuiper Belt plummets almost to zero. It's as if someone drew a line in the cosmic sand and said, "No further." This sudden vanishing act shouldn't happen. According to our models of solar system formation, the Kuiper Belt, a vast ring of debris left over from the birth of the planets, should continue steadily outward, gradually thinning as it merges with the even more distant Oort cloud. But instead, it slams into an invisible wall. The Kuiper Cliff lies roughly 50 astronomical units from the Sun. That's 50 times the distance between Earth and our star. Before this boundary, the Kuiper Belt is teeming with icy bodies like Pluto, Eris, and Makemake. Beyond it, almost nothing. The scarcity of objects is so stark that it can't be explained by observational bias or the limitations of our telescopes. Something has either cleared out the region or prevented objects from forming there in the first place. One leading theory points to the gravitational influence of an undiscovered planet. Perhaps the same elusive planet 9 thought to be shepherding distant orbits. A massive world lurking in the darkness could have swept through the outer Kuiper Belt long ago, its gravity flinging smaller objects inward or ejecting them from the solar system entirely. The problem: even a planet 10 times the mass of Earth would struggle to sculpt such a sharp edge without leaving other obvious traces in the orbits of known objects. Then there's the possibility that the Kuiper Cliff marks the outer limit of the Sun's primordial planetary nursery. In the early solar system, the disk of gas and dust that birthed the planets might have had a finite, well-defined edge, like a cosmic shoreline where the material simply ran out. If so, the Kuiper Belt's abrupt end could be a fossilized relic of that ancient boundary, preserved for billions of years. but this too raises questions. Why wouldn't the disk fade more gradually? And why do some planetary systems around other stars show no such clear-cut borders? A third, more radical idea suggests the cliff might be evidence of a close encounter, a passing star that grazed our solar system in its infancy, stripping away the outer Kuiper Belt like a thief in the night. Simulations show such flybys were possible in the Sun's crowded birth cluster, but pinning down a specific culprit is next to impossible. What makes the Kuiper Cliff so fascinating isn't just the mystery itself, it's the way it forces us to reconsider the history of our own cosmic backyard. Every time we think we've pieced together the solar system story, anomalies like this remind us how much we've yet to learn. Whether the answer lies in a hidden planet, an ancient stellar intruder, or something entirely unexpected, one thing is clear: even in the familiar reaches of our solar system, the universe still has surprises in store. The universe is supposed to expand evenly in all directions, a grand cosmic drift where galaxies slowly separate like dots on an inflating balloon. But in the early 2000s, astronomers stumbled upon something that shattered this elegant symmetry, a phenomenon so unsettling they called it the dark flow. Across billions of light-years, entire clusters of galaxies aren't just drifting apart, they're streaming together in the same direction, as if pulled by some unseen force beyond the edge of everything we know. This discovery came from meticulous studies of galaxy clusters using the Wilkinson Microwave Anisotropy Probe, or WMAP, a spacecraft designed to map the cosmic microwave background. Researchers noticed something bizarre. These clusters weren't just moving with the universe's expansion, they had an extra velocity, a shared motion toward a single point in space near the constellations Centaurus and Hydra. The scale of this motion was staggering. Hundreds of galaxy clusters, each containing thousands of galaxies, were all being tugged in unison at speeds exceeding 2 million miles per hour. And the most chilling part, the source of this pull seemed to lie outside the observable universe. The implications are profound. According to standard cosmology, nothing beyond our cosmic horizon, the 14 billion light-year limit of what we can see, should be able to influence the motion of galaxies inside it. The observable universe is, by definition, a self-contained bubble where everything within it has been causally connected since the Big Bang. But the dark flow suggests something else is out there, something massive enough to warp the fabric of space-time on a scale we can barely fathom. Theories attempting to explain it range from the speculative to the mind-bending. One possibility is that the dark flow is evidence of a neighboring universe, a separate bubble of space-time brushing against our own in the greater multiverse. In this scenario, the gravitational pull of an entire other cosmos with its own stars, galaxies, and perhaps even unfamiliar physics could be reaching across the void, tugging our galaxies toward it like a cosmic magnet. Others propose that the flow might trace back to the chaotic conditions of the early universe. During inflation, the rapid expansion that occurred just after the Big Bang, regions of space might have been stretched unevenly, leaving behind imbalanced gravitational forces that still echo today. Or perhaps the culprit is something even stranger, a defect in the fabric of space-time itself, a cosmic knot left over from the universe's birth, warping the motion of everything around it. Skeptics, of course, argue that the dark flow might not be real at all, that it's an artifact of measurement errors or incomplete data. But follow-up studies, including observations from the Planck satellite, have only deepened the mystery. The signal persists, defying easy dismissal. What makes the dark flow so electrifying isn't just the mystery of what's causing it, it's the way it forces us to confront the limits of our knowledge. If confirmed, it would mean the universe we see is just a small part of something vastly larger, a single ripple in an ocean we're only beginning to sense. And that's the thrill of cosmology. Sometimes the most profound discoveries aren't about finding answers, but about realizing how much bigger the questions truly are. Of all the elements in the periodic table, lithium seems like it should be straightforward, a simple metal with just 3 protons. But this unassuming element is at the heart of one of cosmology's most persistent puzzles. According to our best models of the Big Bang, the early universe should have produced a very specific amount of lithium as it cooled from a searing plasma into the first atoms. The calculations are precise, backed by decades of nuclear physics. There's just one problem. When astronomers measure the lithium content of ancient stars, the numbers don't match. The universe appears to have 2 to 3 times less lithium than our theories predict. This glaring gap, known as the Lithium Problem, isn't just a minor accounting error. It's a direct challenge to our understanding of how the cosmos evolved in its first fiery moments. The mystery begins with Big Bang nucleosynthesis, the process that forged the universe's first light elements in the minutes following its birth. As the newborn cosmos expanded and cooled, protons and neutrons collided and fused, creating hydrogen, helium, and trace amounts of lithium and beryllium. The math behind these reactions is remarkably accurate, so much so that the predicted abundances of hydrogen and helium match observations almost perfectly. But lithium, that's where the story unravels. Ancient stars, which formed from nearly pristine materials shortly after the Big Bang, show only a fraction of the expected lithium in their atmospheres. It's as if someone erased half the lithium from the universe's ledger, and no one knows how. One possible explanation lies in the stars themselves. Could lithium be destroyed or hidden in ways we don't yet understand? Some theories suggest that as these ancient stars churn their interiors over billions of years, lithium sinks from their outer layers into hotter regions where it's fused into heavier elements, effectively vanishing from sight. Others propose that turbulent mixing in stellar atmospheres might dilute lithium concentrations, making them appear lower than they truly are. But even the most sophisticated stellar models struggle to account for the full discrepancy. If stars are eating lithium, they're doing it far more efficiently than physics allows. Then there's the wildcard possibility. Maybe our understanding of the early universe is incomplete. Could unknown particles or forces have altered the nuclear reactions during those critical first minutes? Some physicists speculate that hypothetical particles like actions or variations in the fundamental constants of nature might have skewed lithium production. Others wonder if primordial black holes lurking in the infant cosmos could have absorbed enough lithium-rich material to tip the scales. These ideas push the boundaries of known physics, but the lithium problem is stubborn enough to demand radical thinking. What makes this puzzle so compelling isn't just the missing lithium, it's what it represents. The Big Bang nucleosynthesis model is one of the cornerstones of modern cosmology, a triumph of theoretical and observational alignment. For it to falter on this one element suggests there's a gap in our knowledge, a hidden chapter in the universe's earliest story. Solving it could reveal new physics, reshape our models of stellar evolution, or even uncover processes we've yet to imagine. For now, the lithium problem stands as a quiet but persistent reminder. Even our most successful theories have unresolved edges, places where the universe whispers that there's more to learn. And sometimes the smallest elements hold the biggest secrets. Most nebulae in the universe swirl and billow like cosmic smoke, their shapes sculpted by chaotic stellar winds and explosions. But in the constellation Monoceros, 2,300 light-years from Earth, there's an object that breaks all the rules, the Red Rectangle Nebula. This enigmatic structure lives up to its name, appearing as a near-perfect geometric figure glowing with an eerie crimson hue. Unlike the organic curves of most nebulae, its sharp angles and symmetrical ladder-like rungs look almost artificial, as if someone etched a celestial blueprint across the sky. The Red Rectangle's bizarre form was first spotted in the 1970s, and it's been confounding astronomers ever since. At its heart lies a binary star system, where an aging sun-like star and a smaller, hotter companion orbit one another in a tight dance. As the dying star sheds its outer layers, these ejected materials should form a typical spherical or irregular nebula. Instead, they've arranged themselves into this precise, almost architectural shape. The leading theory suggests that thick disks of dust surrounding both stars act like stencils, funneling the outflowing gas into those distinctive X-shaped patterns and ladder rungs. But how these disks maintain such crisp geometry over vast distances stretching nearly a third of a light year remains a mystery. Then there's the nebula's striking color, a deep red unlike anything else in the cosmos. Most nebulae glow blue from scattered starlight or pink from ionized hydrogen, but the Red Rectangle's hue comes from an entirely different process. Spectroscopy reveals an abundance of complex organic molecules called polycyclic aromatic hydrocarbons, or PAR, carbon-rich compounds that fluoresce under ultraviolet light. These molecules are common in space, but nowhere else do they concentrate in such vivid, monochromatic brilliance. Some researchers speculate that the binary star's unique interactions are cooking these molecules into existence, creating a chemical factory unlike any other. But the real puzzle is why this nebula exists at all. Binary stars aren't rare, and neither are dying stars shedding their outer layers. Yet nowhere else in the observable universe do we see such a perfect geometric structure emerging from this process. Is the Red Rectangle the result of some finely tuned alignment of stellar winds and dust? Or does it hint at undiscovered physics governing how certain stars interact in their final stages of life? What makes this nebula so mesmerizing isn't just its defiance of expectations, it's the way it blurs the line between cosmic chaos and order. Most of the universe's beauty arises from turbulence and randomness, but here, against all odds, nature has produced something that feels almost deliberate. As telescopes like Hubble and JWST continue to study its intricate details, the Red Rectangle stands as a testament to the universe's endless capacity to surprise us. In a cosmos full of swirling mysteries, sometimes the most profound questions come in perfectly straight lines. Imagine a world where the ground beneath your feet isn't rock or ice but diamond. Not just scattered gems, but an entire planet so rich in carbon that a significant portion of its mass could be crystallized into this glittering mineral. That's the mind-bending reality of 55 Cancri E, a scorching hot super-Earth orbiting a star just 40 light-years away. Discovered in 2004, this exotic world defies every expectation of what a planet should be, presenting a cosmic riddle that has scientists rethinking the boundaries of planetary formation. What makes 55 Cancri E so extraordinary isn't just its composition, it's the sheer extremity of its existence. Roughly twice Earth's size but nearly 8 times as massive, this planet orbits so close to its sun-like host star that a single year lasts just 18 hours. Surface temperatures soar above 2,000 degrees Celsius, hot enough to vaporize rock and turn even diamond into a molten sea. Yet despite this inferno, astronomers believe the planet's interior could be packed with crystalline carbon, forged under crushing pressures that defy earthly comparison. The diamond planet hypothesis stems from the unique chemistry of its parent star, 55 Cancri A, which contains nearly twice the carbon-to-oxygen ratio of our Sun. In such a carbon-rich environment, planetary formation takes a dramatic turn. Instead of silicate-dominated worlds like Earth, where oxygen binds with silicon to form rock. Carbon becomes the building block of everything. Under the intense heat and pressure of 55 Cancri's interior, carbon could crystallize into diamond, creating a mantle unlike anything in our solar system. Some estimates suggest up to a third of the planet's mass, equivalent to about 3 Earths' worth of material, might exist in this glittering form. But here's where the mystery deepens. Recent observations have revealed another bizarre twist. 55 Cancri might be shrouded in an atmosphere of vaporized rock. Data from the Spitzer Space Telescope hints at dramatic temperature swings between its day and night sides, implying a thin, volatile envelope of gases like hydrogen, helium, or even silicon monoxide, a substance that would literally rain pebbles in cooler regions. How such an atmosphere persists under the star's relentless radiation is anyone's guess. The enigma of 55 Cancri forces us to confront how little we truly understand about planetary diversity. Most formation models are built on the chemistry of our own solar system, where carbon is relatively scarce. In a carbon-dominated system like 55 Cancri, the rules rewrite themselves. Could there be other diamond worlds lurking nearby? And what might their existence tell us about the range of environments where life in forms we can't yet imagine might arise? For now, 55 Cancri remains a dazzling paradox, a world that challenges our definitions of what a planet can be. Whether it's truly a diamond-studded marvel or something even stranger, one thing is certain. The universe has a flair for the extravagant, crafting worlds so bizarre they seem ripped from the pages of science fiction. And as we keep searching, who knows what other glittering secrets the cosmos might be hiding? If you could zoom out far enough, past the stars, past the galaxies, past even the sprawling clusters of galaxies, you'd see something astonishing. The universe isn't a random scatter of lights. It's a web, a vast, intricate network of luminous filaments stretching across billions of light years, connecting galaxies like beads on a cosmic string. This is the cosmic web, the largest structure in existence, and its origins remain one of the most profound puzzles in modern cosmology. The cosmic web's architecture is breathtaking in its complexity. Threads of dark matter, invisible, mysterious, and outweighing ordinary matter 5 to 1 form the scaffolding. Along these dark tendrils, gas collects, igniting into stars and galaxies at the densest intersections. The result is a tapestry of voids, walls, and filaments, a pattern so vast it defies human intuition. But here's the mystery. How did something so perfectly organized emerge from the chaos of the Big Bang? The leading theory traces the web's birth to the universe's earliest moments. In the first fraction of a second after creation, quantum fluctuations, tiny ripples in the fabric of space-time, were stretched to cosmic proportions by inflation, the universe's explosive initial growth. These ripples became the seeds of structure, regions where gravity would later pull matter together. Over billions of years, dark matter's relentless tug drew gas and dust into its invisible embrace, sculpting the first filaments. Ordinary matter, though just a trace ingredient, followed the dark matter's lead, pooling where the gravitational wells were deepest. Yet the details are maddeningly elusive. Why do filaments have the thickness they do? Why do some regions of the web seem underdeveloped, while others thrum with galaxies? Simulations, like the famous Illustristiangi project, can recreate the web's general shape, but they rely on assumptions about dark matter's behavior, and we still don't know what dark matter actually is. Some filaments in simulations appear too diffuse, while others cluster galaxies more tightly than observed. It's as if we're trying to reconstruct a cathedral from a handful of blueprints with half the pages missing. Even more puzzling are the web's missing baryons, the ordinary matter that should be spread along the filaments but remains largely invisible to telescopes. Hot, diffuse gas in these threads emits faint X-rays, but the numbers don't add up. Where is the rest? Some may hide as ultra-diffuse plasma, too faint to detect. Others might lurk in rogue clumps ejected by galactic winds. Or perhaps our instruments simply aren't sensitive enough yet to catch the whispers of this hidden material. The cosmic web isn't just a curiosity, it's the stage upon which the story of the universe plays out. Galaxies are born where filaments intersect, their fates dictated by the web's unseen architecture. Understanding its origins could reveal how dark matter shapes the cosmos, why galaxies form where they do, and even how the universe will evolve in the eons to come. New telescopes, like the upcoming European Space Agency's Euclid mission, aim to map the web in unprecedented detail, tracing its filaments across millions of galaxies. Meanwhile, experiments hunting for dark matter particles inch closer to decoding the invisible skeleton holding it all together. Every thread we unravel brings us closer to answering a question as old as cosmology itself. How did emptiness become everything? The cosmic web is more than a structure. It's a living record of the universe's grandest transformation, written in dark matter and starlight. And we're only just beginning to read it. In the vast menagerie of cosmic oddities, few discoveries are as puzzling or as aptly named as the unicorn. Nestled just 1,500 light-years from Earth, lurking in the constellation Monoceros, this enigmatic object holds a unique title, the smallest known black hole in the universe. With a mass just 3 times that of our Sun, the unicorn defies everything we thought we knew about how these gravitational monsters form. Most black holes fall into 2 categories: stellar mass black holes, born from collapsing stars at least 20 times heavier than the Sun, or supermassive behemoths millions to billions of times more massive, lurking in galactic centers. The unicorn fits neither mold. It's a cosmic runt, a black hole that shouldn't exist, yet here it is, quietly warping space-time in our cosmic backyard. What makes the unicorn so baffling isn't just its size, it's the way it was found. Unlike most black holes, which reveal themselves by devouring nearby gas or bending light around them, this one was detected through its subtle gravitational dance with a neighboring red giant star. The star's light periodically stretches and compresses, as if an invisible companion is tugging on it like a puppeteer's string. By measuring these minute shifts, astronomers deduce the presence of a compact object too small to be a neutron star, yet too massive to be anything but a black hole. It's a ghostly waltz, one that hints at an entire hidden population of similar objects lurking undetected across the galaxy. The discovery throws a wrench into stellar evolution models. Conventional wisdom says stars between about 8 and 20 solar masses should explode as supernovae, leaving behind neutron stars, not black holes. The unicorn's existence suggests that either our understanding of supernova physics is incomplete, or there's an entirely new pathway for black hole formation. Some theorists speculate that in rare cases, lower mass stars might collapse directly into black holes without a supernova, a process called direct collapse. Others wonder if the unicorn could be the remnant of a merged binary star system, its mass cobbled together from smaller, denser predecessors, but the implications stretch far beyond this one oddity. If the unicorn isn't alone, if the galaxy is teeming with similar small black holes, it could solve another cosmic mystery, the missing black hole problem. Gravitational wave observatories like LIGO have detected mergers of surprisingly heavy black holes, far larger than expected for typical stellar remnants. Where did these giants come from? One possibility is that they grew by snacking on a buffet of smaller black holes like the unicorn, a hidden underclass of gravitational traps silently shaping the universe's violent mergers. The hunt is now on to find more of these elusive objects. New techniques like precision measurements of star wobbles or subtle distortions in background starlight could unveil dozens or even hundreds of similar black holes hiding in plain sight. Each discovery would rewrite the rules of stellar death, forcing us to rethink how stars live, die, and transform into the universe's most extreme objects. The unicorn is more than just a cosmic curiosity. It's a key to unlocking secrets about the life cycles of stars and the hidden architecture of our galaxy. Its very existence whispers that the universe still has surprises tucked away, even in the most familiar corners of the sky. And as we peer deeper into the darkness, who knows what other mythical beasts might be waiting to reveal themselves, far beyond the orbit of Neptune, where sunlight is a mere whisper and temperatures hover near absolute zero, a group of cosmic misfits refuses to play by the rules. These are the extreme Trans-Neptunian objects, icy bodies with orbits so wildly tilted and stretched that they defy conventional explanations. Some swing so far from the Sun that a single trip around it takes tens of thousands of years, their paths tracing bizarre, elongated ellipses that seem almost purposeful in their defiance. Others orbit at steep angles, tilted as much as 90 degrees relative to the orderly plane of the solar system. These aren't just statistical outliers, they're cosmic rebels, and their strange behavior might be the strongest clue yet that something massive is lurking in the frigid darkness of our solar system's outer reaches. The mystery began in earnest in 2003 with the discovery of Sedna, a dwarf planet whose looping 11,000-year orbit takes it from 76 astronomical units at its closest to a staggering 936 astronomical units at its farthest. For context, Pluto never strays beyond 49 astronomical units from the Sun. Sedna's path made no sense. No known gravitational force in the solar system should have placed it on such a distant, lonely trajectory. Then came 2014's discovery of 2012 VP 113, nicknamed Biden, with an orbit even more extreme. These objects, along with half a dozen others, share a peculiar trait. Their closest approaches to the Sun cluster in a way that suggests an unseen hand has herded them into these peculiar orbits. The leading explanation, a hidden planet, perhaps 5 to 10 times the mass of Earth, orbiting hundreds of astronomical units from the Sun. This hypothetical world, dubbed Planet 9, would exert just enough gravitational influence over millions of years to sculpt these odd orbits. Computer simulations show that such a planet could explain the observed clustering with astonishing precision. But there's a catch: no telescope has yet spotted this elusive giant. The search is like looking for a single dim light bulb in a city the size of a continent, with the added complication that we don't even know which street it's on. Yet Planet 9 isn't the only possible answer. Some theorists propose an alternative culprit, a primordial black hole, no larger than a grapefruit but with the mass of a planet, warping the orbits of these distant objects with its intense gravity. Others suggest the collective gravity of many smaller Kuiper Belt objects, or even a close stellar fly by billions of years ago, could have scattered these bodies into their strange paths. Each theory comes with its own challenges. A black hole would be even harder to detect than a planet, while the stellar flyby scenario struggles to explain why the orbits remain clustered rather than randomized. What makes this mystery so compelling is the way it forces us to confront the limits of our knowledge. The outer solar system is the last great frontier of planetary exploration, a region so vast and dimly lit that it could hide almost anything. Every new discovery, like 2021's detection of object 541-432 Lelikuhanua, with the most elongated orbit of any known solar system body, adds another piece to the puzzle. Whether the answer is Planet 9, a black hole, or something even stranger, one thing is certain: the Kuiper Belt's misfits are telling us a story. We just haven't learned to read it yet. The search continues with next-generation telescopes like the Vera-C Rubin Observatory poised to scan the skies with unprecedented sensitivity. Each new observation could be the key that unlocks this cosmic riddle, revealing whether our solar system harbors a hidden giant or if we need to rewrite the rules of planetary dynamics entirely. Until then, these strange orbits remain a tantalizing clue, a gravitational signature etched across the frozen depths of space, waiting to be deciphered. We like to think of dark energy as a constant force, an unchanging presence steadily pushing the universe apart. But what if it's not? What if this mysterious energy, which makes up nearly 70% of the cosmos, is actually shifting over time, growing stronger or weaker in ways we never anticipated? This provocative idea, known as phantom dark energy, isn't just a tweak to the equations, it's a potential revolution in how we understand the universe's ultimate fate. For decades, the reigning model has treated dark energy as a cosmological constant, a steady pressure embedded in space itself, first proposed by Einstein and later revived to explain the universe's accelerating expansion. The beauty of this idea lies in its simplicity. Dark energy acts like a fixed background force, neither increasing nor decreasing as the cosmos evolves. But cracks are starting to show in this tidy picture. When astronomers compare measurements of the universe's expansion rate at different epochs, from ancient supernova to modern galaxy surveys, some datasets hint that dark energy's push might not be perfectly uniform. It could be fluctuating ever so slightly across cosmic time. The implications are staggering. If dark energy isn't constant but instead grows stronger, a scenario dubbed phantom dark energy, the universe's fate veers into science fiction territory. Instead of a slow, cold expansion where galaxies fade into isolation, phantom energy would accelerate exponentially, eventually tearing apart everything from galaxy clusters to atoms themselves in a catastrophic Big Rip. On the other hand, if dark energy weakens over time, the universe's expansion could slow, potentially reversing into a big crunch where everything collapses back into a singularity. The evidence is still tentative, buried in the noise of observational data. Some studies of Baryon acoustic oscillations, the faint, fossilized ripples from the early universe, show patterns that slightly favor evolving dark energy. Others, like the Dark Energy Survey's painstaking maps of millions of galaxies, still align with the constant model. The challenge is that these deviations are subtle, often overshadowed by measurement uncertainties and cosmic variance. It's like trying to detect whether a river's current is strengthening by studying a handful of drifting leaves. What makes this mystery so electrifying is how deeply it cuts to the core of cosmology. Dark energy isn't just another puzzle piece, it's the dominant ingredient shaping the universe's destiny. If it's truly dynamic, we might need to rewrite the story of everything from the Big Bang's aftermath to the far future. Some theorists speculate that phantom behavior could hint at entirely new physics, like a fifth fundamental force or an interaction between dark energy and dark matter. Others wonder if it's evidence of a multiverse where our cosmic patch has unique properties unlike other regions of reality. The quest for answers is driving next-generation experiments. The Euclid Space Telescope, launched in 2023, is mapping billions of galaxies to trace dark energy's influence with unprecedented precision. Meanwhile, ground-based projects like the Vera C. Rubin Observatory's legacy survey of space and time will scour the sky for supernova, galaxy shapes, and other cosmic yardsticks that could reveal dark energy's true nature. For now, phantom dark energy remains a tantalizing what-if, a whisper in the data that could either fade into statistical noise or ignite the next great paradigm shift in physics. Whether it's real or not, the mere possibility forces us to confront how little we truly grasp about the forces governing our universe. And that's the thrill of cosmology. Sometimes, the most profound discoveries begin with a hunch that the rules we've always trusted might just be a little more flexible than we thought. Mars has always been a world of contradictions, a frozen desert with ancient river valleys, a lifeless landscape that somehow teases us with the possibility of life. But nothing embodies this paradox more than the mysterious methane that comes and goes in the planet's thin atmosphere. Unlike Earth, where methane is constantly replenished by living organisms and geological activity, Mars' methane behaves like a ghost, appearing in sudden, unpredictable spikes before vanishing without a trace. These fleeting whiffs have sparked one of the most heated debates in planetary science. Is this gas a sign of hidden microbes beneath the rust-colored soil, or just the breath of an ancient, geologically active world? The mystery began in earnest in 2003, when the European Space Agency's Mars Express orbiter detected traces of methane in the planet's atmosphere. Since then, NASA Curiosity rover has repeatedly sniffed out methane in Gale Crater, sometimes in bursts 10 times stronger than background levels. These spikes are baffling because methane shouldn't last long in the Martian atmosphere. Sunlight and chemical reactions should break it down within a few hundred years. So why do we keep detecting it? Something somewhere must be actively producing or releasing it. The biological explanation is the most tantalizing. On Earth, the vast majority of methane comes from living organisms, from bacteria thriving in oxygen-free environments like swamps and cow stomachs to vast underground reservoirs of ancient microbial life. If microbes exist deep beneath Mars' surface, shielded from radiation in briny aquifers, they could be producing methane as a byproduct of their metabolism. It's a thrilling possibility, one that would rewrite our understanding of life's resilience. But biology isn't the only contender. Mars geology might hold the key instead. The planet is far from dead. Volcanic activity, though rare, could still release methane from deep underground. Even without active volcanoes, a process called serpentinization, where water reacts with certain rocks, can produce methane abiotically. Then there's the wild card. Ancient methane trapped in ice like clathrate compounds could be slowly seeping out as temperatures shift over millennia. The trouble is, no one's found definitive proof of any of these processes happening today. The plot thickens when you consider how inconsistently the methane appears. Some instruments, like the Trace Gas Orbiter, have failed to detect it at all from orbit, while Curiosity's ground-level readings show dramatic but localized spikes. This discrepancy has led to another radical theory. Maybe the methane isn't lingering in the atmosphere as expected. It could be destroyed far faster than we thought, perhaps by electrostatic dust storms or some unknown chemical process. The stakes couldn't be higher. If the methane is biological, it would be the first concrete evidence of life beyond Earth. If it's geological, it could point to unexpected underground activity, reshaping our understanding of Mars as a dynamic world. Future missions like NASA Mars Life Explorer aim to drill deeper than ever before, hunting for answers in the subterranean layers where sunlight and harsh surface conditions can't reach. Until then, Mars keeps its secrets close, offering us just enough methane to fuel our curiosity, but never enough to settle the debate. What makes this enigma so gripping isn't just the question of life, It's the reminder that Mars, for all its barren appearance, is still a world of surprises. Every new detection, every contradictory measurement pulls us deeper into the mystery, proving that even our closest planetary neighbor still has stories left to tell. And whether the answer lies in ancient volcanoes or hidden microbes, one thing's certain: solving the methane riddle will redefine our place in the cosmos. Every story has a beginning, but what if ours wasn't a beginning at all? What if the Big Bang, the fiery birth of our universe, wasn't the first chapter, but the aftermath of something far stranger? This is the radical premise behind one of cosmology's most mind-bending ideas, that our entire universe might have been born from the collapse of a black hole in a higher dimensional reality. It's a theory that turns conventional wisdom on its head, suggesting that the singularity at the heart of the Big Bang wasn't just a point of infinite density. It could have been the core of a black hole from another cosmos. The idea hinges on the eerie similarities between two of physics' most enigmatic phenomena: the singularities inside black holes and the singularity from which our universe expanded. Both represent points where the known laws of physics break down, where density becomes infinite and space-time curves beyond comprehension. In the 1970s, physicists like Stephen Hawking and Roger Penrose explored how black holes might contain hidden pathways to new universes, regions where collapsing matter doesn't just vanish but rebounds as a new cosmic genesis. Fast forward to modern string theory, and this concept takes on even wilder dimensions. Some models suggest our three-dimensional universe could be a membrane, or brain, floating in a higher dimensional space, with the Big Bang triggered when a black hole in that parent universe imploded, ejecting our reality like a cosmic seed. But how could a black hole, an object known for trapping everything, even light, spawn an entire expanding universe? The key might lie in the nature of singularities themselves. At the quantum level, the crushing gravity of a black hole's core could reach a point where it rebounds, transforming collapse into expansion. Imagine squeezing a spring to its limit. The energy has to go somewhere. In this scenario, the black hole's implosion flips into the Big Bang's explosion, with the infant universe inheriting properties like its total mass and initial smoothness from the black hole's structure. This could even explain why our universe appears finely tuned for life. The physics of the parent black hole might have set the conditions for our cosmic constants. Not everyone is convinced, of course. Critics point out that this theory requires speculative physics, like extra dimensions or exotic quantum gravity effects that we can't yet test. The traditional Big Bang model, for all its unanswered questions, at least fits snugly within the framework of general relativity and observable evidence like the cosmic microwave background. Then there's the causality problem. If our universe came from a black hole in another reality, what created that universe? Its turtles all the way down, a regression that leaves some scientists cold. Yet the black hole cosmology hypothesis refuses to fade away, partly because it offers elegant solutions to stubborn puzzles. For instance, it could explain why the early universe was so remarkably uniform, the result of a black hole's event horizon, scrambling, infalling matter into a smooth, high-entropy state before the rebound. It might also shed light on dark matter, which could be remnants of the parent universe's gravitational imprint. Most provocatively, it suggests that black holes in our universe might themselves be cosmic wombs, each harboring the potential to birth new realities in their depths, a fractal multiverse where every collapse begets a new expansion. The challenge, as always, is evidence. If our universe truly carries fingerprints of its black hole origins, they'd be subtle, perhaps hidden in the pattern of gravitational waves from the earliest moments, or in anomalies in the cosmic microwave background. Future telescopes, like the proposed Laser Interferometer Space Antenna, could hunt for these clues, Until then, the theory remains a dazzling thought experiment, a reminder that the universe's greatest mysteries might not just lie ahead of us, but behind us, in the shadow of a singularity we can never see. Whether this idea ever graduates from hypothesis to fact, it underscores a profound truth. The more we learn about the cosmos, the more boundaries blur between beginnings and endings, destruction and creation. A black hole's appetite might just be the other side of a universe's birth cry, two sides of a coin we're only beginning to flip. Stars die spectacularly. When massive ones reach the end of their lives, they don't fade quietly. They explode in blinding supernova, briefly outshining entire galaxies and scattering the elements that make up planets and life across the cosmos. These explosions are supposed to be cosmic constants, predictable milestones in the life cycle of stars. But here's the catch: astronomers aren't seeing nearly as many as they should. Based on the number of massive stars in our galaxy and others, scientists expect to observe around 3 supernovae per century in a galaxy like the Milky Way. Yet the actual count falls woefully short, leaving researchers scrambling to explain where these missing fireworks have gone. One possibility is that we're simply missing them. Supernova can be sneaky, especially if they're obscured by thick clouds of dust or gas. Imagine a firework bursting behind a dense fog. From our vantage point, the light might be dimmed or distorted beyond recognition. Some supernova could be hiding in the crowded, dusty cores of galaxies where telescopes struggle to peer through the cosmic haze. Infrared surveys, which can penetrate dust better than visible light, have turned up a few previously hidden explosions, but not nearly enough to close the gap. Then there's the more intriguing option: maybe these stars aren't exploding at all. Some massive stars might skip the supernova stage entirely, collapsing directly into black holes without the fanfare of a luminous blast. This direct collapse scenario would leave behind little to no visible trace, just a silent gravitational pit where a star once shone. Supporting this idea are the growing number of disappearing stars objects that vanish from telescope observations without the expected explosive send-off. In one famous case, a red supergiant star named N694 in the nearby galaxy Messier 101 abruptly disappeared in 2008, leaving astronomers debating whether it fizzled into a black hole without the usual fireworks. But why would stars cheat death like this? The answer might lie in their internal dynamics. Stars on the heavier end of the spectrum, those 20 times more massive than the Sun or larger, could become so unstable in their final moments that their cores implode catastrophically, swallowing the star's outer layers before they can erupt outward. Alternatively, intense stellar winds or binary interactions might strip away enough material before collapse to dampen the explosion, resulting in a whimper instead of a bang. The implications ripple far beyond stellar astronomy. Supernova are cosmic recyclers, forging heavy elements like iron, gold, and uranium and scattering them into space. If massive stars are vanishing quietly, it could mean the universe's chemical enrichment is happening differently than we thought. Entire generations of stars might be contributing less to the galactic supply chain than our models predict, subtly altering the recipe for future planets and life. The hunt for answers is driving new observational strategies. Automated sky surveys like the Zwicky Transient Facility scan the heavens nightly for sudden flashes, while next-generation telescopes like the Vera C. Rubin Observatory promised to catch even the faintest, fastest-fading explosions. Meanwhile, theorists are refining models of stellar death, probing the precise conditions that could tip a star towards silent collapse over spectacular detonation. What makes this mystery so compelling isn't just the missing explosions, it's what they reveal about the universe's unpredictability. even something as seemingly straightforward as a star's death can defy expectations, reminding us that the cosmos still holds surprises in its darkest corners. Whether the solution lies in better observations, revised physics, or something entirely unforeseen, one thing's certain: the universe has a way of keeping its most dramatic exits hidden from view. For all our grand theories about the universe's birth, its ultimate fate remains one of the most hotly debated questions in cosmology. Will the cosmos continue expanding indefinitely, fading into an endless, frozen darkness? Or will gravity eventually reverse the expansion, collapsing everything back into a fiery singularity? Or perhaps the most unsettling possibility: could the fabric of space-time itself tear apart in a catastrophic finale? The answer hinges on a cosmic tug-of-war between two invisible forces we barely understand: dark energy, which drives the universe apart, and dark matter, which pulls it together. The simplest scenario, known as the Big Freeze, is also the most widely accepted. In this model, dark energy, the mysterious force accelerating the universe's expansion, remains constant, steadily pushing galaxies farther apart until they're isolated islands in an ever-growing void. Stars will burn out, black holes will evaporate, and over trillions of years, the universe will settle into a state of near-perfect equilibrium, a featureless expanse where even time loses meaning. It's a quiet, almost poetic end, but one that raises unsettling questions. Why is dark energy's strength precisely tuned to create this outcome? If it were slightly stronger or weaker, the universe's fate would look radically different. That's where the alternative theories get wild. Some models suggest dark energy isn't constant at all but evolves over time. If it grows stronger, a scenario dubbed phantom dark energy, it could eventually overwhelm every binding force in the cosmos. First, galaxy clusters would rip apart, then individual galaxies, then stars, planets, and even atoms themselves. This big rip would be a violent, chaotic end, shredding the universe's structure in a final, unimaginable cataclysm. On the other hand, if dark energy weakens, gravity might regain the upper hand. The expansion could slow, halt, and reverse, collapsing all matter back into a singularity, a big crunch, mirroring the Big Bang in reverse. Some theorists even speculate this cycle could repeat indefinitely, with universes expanding and contracting in an endless loop. Then there's the wild card: quantum fluctuations. In a universe that persists for eternity, even the most improbable events become inevitable. Some models suggest that quantum tunneling could spawn new Big Bangs in the distant future, creating fresh universes in the ashes of our own. It's a dizzying thought that even in the coldest, darkest reaches of time, the seeds of new cosmic beginnings might lie dormant. What makes this mystery so urgent isn't just academic curiosity. It's that we might find answers sooner than we think. Next-generation telescopes like the Vera C, Rubin Observatory, and the Nancy Grace Roman Space Telescope are mapping the universe's expansion with unprecedented precision, hunting for subtle clues about dark energy's true nature. Meanwhile, experiments probing the cosmic microwave background could reveal whether the universe's geometry hints at an eventual collapse or endless expansion. The stakes couldn't be higher. The universe's fate isn't just a distant abstraction, it's a reflection of the fundamental laws that govern everything from the smallest particles to the largest structures in existence. Whether the cosmos ends in ice, fire, or something stranger, one thing's certain: the answer will rewrite our understanding of reality itself. And until then, the question lingers, a humbling reminder that for all we've learned, the universe's final chapter remains unwritten. From unexplained signals crackling across the cosmos to invisible forces shaping galaxies, These 30 interstellar puzzles aren't just scientific roadblocks, they're invitations. Each one is a doorway into the unknown, reminding us that for every question we answer, the universe reveals 10 more. Think about it: the wow signal's fleeting whisper, dark matter's ghostly grip, the Great Attractor's relentless pull. These aren't just anomalies scribbled in astronomers' notebooks. They're cosmic breadcrumbs, clues that could rewrite textbooks or even reveal entirely new laws of physics. What's truly exhilarating is how these mysteries fuel progress. Every time a telescope fails to spot Planet 9 or a lab comes up empty in the hunt for dark matter particles, scientists don't just shrug, they innovate. The search for fast radio bursts led to telescopes that mapped the universe's hidden scaffolding. The Enigma of Tabby star sparked new ways to analyze starlight for signs of alien engineering. Even the frustrating silence of the Fermi Paradox pushes us to build better detectors, refine our definitions of life, and question assumptions we didn't realize we'd made. And let's not forget the bigger picture. These puzzles aren't just academic exercises, they're mirrors reflecting our place in the cosmos. The more we learn about galactic voids or phantom dark energy, the more we confront humbling truths, that we're stardust trying to understand itself, that our universe might be one of countless others, or that the answers we seek could be hiding in dimensions we can't yet perceive. So what's next? With breakthroughs like the James Webb Space Telescope peering deeper into space and time than ever before, gravitational wave detectors tuning into cosmic collisions, and AI sifting through mountains of data for hidden patterns, we're on the verge of discoveries we can't yet imagine. Maybe one of these 30 mysteries will crack open first, or perhaps the next great cosmic riddle is still waiting to reveal itself, lurking just beyond the edge of our current understanding. That's the thrill of exploration. Whether you're an astrophysicist or a casual stargazer, these questions remind us that the universe isn't just stranger than we suppose, it's stranger than we can suppose. So keep looking up, keep questioning, and most of all, stay curious. Because the greatest discoveries often begin with two simple words: wait, that's odd. If these cosmic conundrums left you as awestruck as they did us, drop your favorite mystery in the comments. Is it Oumuamua's impossible acceleration, the eerie silence behind the Fermi Paradox, or something we didn't even cover? Let's nerd out together, and for more deep dives into the universe's unsolved puzzles, hit subscribe so you never miss an update. The cosmos has plenty more secrets to share, and we're just getting